Now, next topic, that is Ampere's circuital law. Say, in electrostatics, we discussed Gauss's law. Using Gauss's law, one can calculate the electric field due to a symmetric charge distribution. And in Gauss's law, we consider a closed surface, which is called Gaussian surface. So, using Gauss's law, one can find the electric field at any point due to symmetric charge distribution. Similarly, using Ampere's circuital law, one can find the magnetic field at any point due to symmetric current distribution. Now, in Ampere's circuital law, we consider the open surface with boundary, and the boundary of that surface, that is considered as Amperian loop, to which Ampere circuital law is applied. And here the currents which are passing through that particular surface, or we can say from the Amperian loop, those currents we have to take in consideration. Now see here, suppose as shown in this figure, through the surface with this boundary as shown in the figure, the currents passing are I1, I2 and I3. Now, with the help of Ampere's circuital law, you can easily calculate the magnetic field at a point due to this current distribution. And Ampere's circuital law, that is given by the equation integration B dot dl, and this integration that should be carried out over the Amperian loop. So integration B dot dl, that is equal to mu 0 sigma I. Sigma I, that is the net current passing through the surface enveloped by Amperian loop. This is very important to understand. See, at present here all the currents are in the same direction. So simply we can say the net current passing through this surface, that is I1 plus I2 plus I3. But see here, suppose we consider another case. Here the open surface, that is this one, and here its boundary, that is represented in the figure. So this open surface is enclosed by this boundary in the direction shown by arrow. એટલે આ એરો મેં જે રીતે બતાવ્યા છે એ રીતે એમ્પિરિયન લૂપ એ બાઉન્ડ્રી એ સરફેસને એન્ક્લોઝ કરે છે. Now here suppose total 5 currents are there, I1, I2, I3, I4 and I5, and the directions of the currents are represented here. So first thing, you have to consider only those currents which are passing through the Amperian loop. The current which one is outside the loop, that will not be taken in consideration, exactly like Gauss's law. In Gauss's law, the charge which is inside the Gaussian surface, that we consider only. The charge outside the Gaussian surface is not taken in consideration. But then also the electric field obtained by Gauss's law, that is due to entire charge distribution, exactly like that. Here also, the magnetic field obtained using Ampere's circuital law, that will be due to entire current distribution. Now, if you want to calculate the net current passing through this loop, then you have to take algebraic summation of all these currents. But which currents we have to take positive and which we have to take negative? So here, again, we have to use right hand rule. We have to place our fingers in the direction of the enveloping loop. At present, the loop enveloping the surface, that is in anti-clockwise direction. See the arrows represented here in anti-clockwise direction. So if we place the fingers in the direction of the enveloping loop, then the currents which are in the direction of the thumb, that you have to take positive, and opposite currents that you have to take negative. What the idea? So in our case, I1 and I2 will be positive, I3, I4 will be negative. So in this particular case, you can write sigma I, that is equal to I1 plus I2 minus I3 minus I4. So in this way, you have to take this sigma I. This is the Ampere circuital law. Clear? Now, how to choose the Amperian loop? So here, we have to choose the Amperian loop such that at each point of the loop, either B is tangential to the loop and is a non-zero constant B, or B is normal to the loop, or B vanishes at each and every point on the loop. In that way, you have to consider the Amperian loop. Clear to all of you?